feeling when you're staring at a physics problem, not because you don't understand the concepts, but because the math looks like some unbreakable alien code? It is a massive pain point, especially for aspiring medical students tackling those complex numericals for the NEET exam. You get the theory, right? But the calculation just completely trips you up. Well, today we're going to fix that. We are building the ultimate physics toolkit, giving you exactly what you need to decode these problems with absolute confidence. Okay, let's dive into this. Listen to this really powerful metaphor from physics instructor Amin Mathur. He says, mathematics is the language of physics. If you go to a foreign country and don't know the language, can you communicate? No. Honestly, this completely reframes the challenge. We really need to stop viewing math as this annoying obstacle standing in the way of a good grade. Instead, it's the very communication tool we use to speak to and understand the universe. Once you learn the grammar and the vocabulary of this language, physics stops being a struggle, and it starts becoming this incredible conversation. So here is our roadmap for today. We'll start with the language of physics, then unlocking logarithms, followed by the binomial shortcut. After that, we are taming trigonometry, and finally, decoding slope. Let's get right into section 1, the language of physics, and specifically our algebraic foundations. Look, before we can even think about using advanced tools to solve intense medical physics numericals, we have to learn the foundational alphabet. It all begins right here. Physics relies entirely on algebraic foundations. Think of your basic algebraic identities, expanding formulas or correctly managing exponents. Like if you have x squared multiplied by x to the power 5, you need to instantly know that becomes x to the power 7. If you can't confidently manipulate those basics, the advanced formulas just won't hold up. This is our absolute baseline. Moving right along to section 2, unlocking logarithms to solve calculations. Let's see how this builds, because physics loves to throw massive, endless calculations at us. Before calculators, people obviously needed a way to shrink these gigantic numbers, which is exactly where logarithms come in. There are two main types you're going to encounter, the common log and the natural log. Now, you're probably pretty comfortable with the common log, the one that uses a base of 10, but in physics, we constantly run into the natural log, which uses a base of e, also known as Napier's constant, and you'll usually see it written out as ln. The real issue here is that we mostly just memorize values for the base 10 log, which leaves us completely stuck when an equation hands us a natural log. So how do we bridge that gap? Well, enter the magic trick, 2.303. Seriously, lock this number into your brain right now. It is the ultimate shortcut factor. Anytime you're faced with a natural log, you simply multiply your common log by 2.303. And just like that, you've converted an unsolvable base e problem into a totally familiar base 10 calculation. So why does this matter practically? Why should you care? Well, take thermal physics. When you calculate the isothermal work done by a gas, the original formula actually uses a natural log. But to actually solve the numerical on an exam, you rely on this exact conversion. We use the formula W equals 2.303 times nRT times log V2 over V1. That 2.303 is literally the key that allows you to find the answer. All right, on to section 3, the binomial shortcut for simplifying roots. Let's keep this momentum going. We have all been there. You perfectly applied the physics concepts, and then, right at the finish line, you hit a total brick wall. How on earth do you calculate the square root of 0.99 without a calculator? In a high-pressure exam environment, it is incredibly frustrating to abandon a totally correct problem just because of a messy final decimal. But don't worry, there is a brilliant way out of this. Now, what's really interesting about this is how the binomial approximation turns an impossible square root into basically first-grade arithmetic. Here are the 3 simple steps. Step 1, format the number. We just rewrite 0.99 as 1 minus 0.01, and since it's a square root, we raise it to the power of 1/2. Step 2, apply the shortcut. Because 0.01 is such a tiny number compared to 1, we can use the approximation rule. Basically, 1 minus x to the power of n is approximately equal to 1 minus n times x. You literally just pull that exponent down to the front. Step 3, solve. It simply becomes 1 minus 1/2 times 0.01. From there, the answer is an absolute breeze. And the value of the shortcut is immense. It's not just for cleaning up messy decimals. This mathematical tool is exactly how we derive vital physics formulas. Take gravitation, for example. When we want to find the effect of gravity at a specific height that's under 320 kilometers, we use this exact binomial expansion to get the formula g prime equals g times 1 minus 2h over r. You aren't just solving basic arithmetic here. You are literally proving the laws of physics. Okay, section 4, taming trigonometry. We're going to finally sort out those angles and sines. Let me let you in on a little academic secret, the Pythagorean triplet. A Pythagorean triplet is a set of 3 integers, like 3, 4, and 5, that perfectly satisfy the Pythagorean theorem. But here is the real trick for physics. This specific 3, 4, 5 ratio corresponds to exact, highly common angles of 37 degrees and 53 degrees. The largest side, 5, is always opposite the largest angle, the 90-degree angle. The middle side, 4, is opposite the 53-degree angle. And the smallest side, 3, is opposite the smallest angle, the 37-degree angle. Memorizing this relationship instantly resolves some of the most painful mechanics calculations you'll encounter. And this brilliantly illustrates how we handle those tricky positive and negative signs, the ASTC rule. Or as some like to remember it, add sugar to coffee. This simple grid permanently eliminates mistakes when assigning signs across the 4 quadrants. In the first quadrant, A stands for all, meaning all trigonometric functions are positive. In the second quadrant, S tells us only sine is positive. In the third, T means tangent is positive. And in the fourth quadrant, C means only cosine is positive. Commit this to memory and you'll literally never miss a sign convention again. Just a really quick note on trigonometry unit conversion before we move on. 180 degrees is exactly equal to pi radians. They are simply 2 ways of expressing the exact same angle. Keep this equivalence locked in your head and you'll effortlessly switch back and forth between degree and radian measurements. Finally, section 5, decoding slope and visualizing the math. Reading graphs and understanding coordinate geometry is absolutely vital. It's how we visualize physical phenomena, especially when we get into thermodynamics and motion. I want you to treat these 4 methods as 4 distinct weapons in your toolkit. Depending on what data a problem gives you, you've got 4 ways to find a slope. First, if you have the angle, just use tangent theta. Second, if you have 2 points on a graph, use the coordinates, y2 minus y1 over x2 minus x1. Third, you can look at the length change, which is simply delta y divided by delta x. And finally, the most advanced tool, differentiation, finding dy over dx. So, the crucial point is this. Slope is exactly equal to the first derivative, dy over dx. By taking the derivative of an equation with respect to a variable, you are literally finding the slope of that line. This is the beautiful, powerful link where basic coordinate geometry plugs straight into calculus, giving you the ability to find the exact rate of change at any given millisecond. We've covered a ton of ground today, from algebraic foundations to binomial approximations, all the way to derivatives. So I'll leave you with this thought. If mathematics is simply a language, what physical phenomenon will you decode first with your new toolkit? Remember, math is not your enemy. It's the ultimate cheat code to understanding how the universe works. Take these tools, practice them, and watch how physics completely opens up to you. Thanks for joining me on this explainer, and keep learning. If you're a focused learner looking to completely transform how you tackle complex scientific problems, you are in exactly the right place. Today, we're unlocking what I like to call the ultimate cheat codes for physics. We're going to bridge that agonizing gap between knowing the theory and actually getting the final answer. Let's just start with a hard truth. Trying to do physics without a solid grasp of basic math, it's exactly like visiting a foreign country without knowing a single word of the local language. I mean, you might have a map, you might know where you want to go, but you just can't converse with the environment around you. Math is the language of physics. Without it, honestly, you're bound to get lost. Okay, let's dive right into this. Here's our roadmap for today. First, we'll look at the language of physics. Then, we're demystifying logarithms, looking at some binomial approximation hacks, exploring the magic of triplets, and finally, mastering the ASTC rule. Starting off with section 1, the language of physics. So before we tackle any complex equations, we really need to establish the foundational mindset required to survive high-stakes exams. And look, I know the exact pain point so many of us have experienced. You know the core physics concepts, right? You set up a free body diagram, you apply Newton's laws perfectly, you do literally 99% of the problem right, and then you fail at the final messy calculation. It is incredibly frustrating to lose marks, not because you don't know the physics, but just because a nasty square root or some weird fraction tripped you up at the finish line. Well, that stops today. Moving on to section 2, demystifying logarithms. This brings us to our first major tool in the toolkit, which is basically the ultimate calculation reducer. Now, I know a lot of people see the word log and instantly panic, but fundamentally, a logarithm is just a mathematical tool. It acts as the reverse of an exponent. Historically, before we all had computers in our pockets, logs were invented for one brilliant purpose: to take these multi-page, incredibly painful calculations and drastically reduce them into short, solvable addition and subtraction equations. It's really just an elegant simplification tool. Now, what's really interesting about this is the contrast between the two types of logs you'll actually encounter in physics. On one hand, you have the common log, which uses base 10, and that's often just written as log of x. And then you have the natural log, which uses base e, that's Napier's constant, setting roughly at 2.71, and we write that as ln of x. So what's the problem? Well, most of us are only comfortable calculating with base 10, but nature and equations like the work done in an isothermal process absolutely love to use the natural log. So the crucial point here is this magic number, 2.303. Think of this as your cheat code multiplier. Whenever you're handed a natural log in thermal physics, or anywhere else really, and you need to solve it using the common base 10 log values that you actually know, you just multiply your base 10 log by 2.303. It bridges the gap instantly. Seriously, memorize this number. It is going to save you massive amounts of time. All right, let's jump into section 3, binomial approximation hacks. Let's shift gears to what is arguably the single most powerful weapon for surviving competitive exams without a calculator. Just picture this terrifying scenario for a second. You're staring at a really messy square root, something like the square root of 25.01, and you don't have a calculator. The clock is ticking. It's an absolute nightmare, right? Well, here is your elegant savior, the binomial hack. By manipulating the number into a very specific format, 1 plus x to the power of n, you can actually solve it mentally in seconds. Okay, so here's the exact actionable checklist to pull off this hack. Step 1, and honestly, this is where most people fail. You absolutely must factor out the large number to leave a strict 1 inside the bracket. For 25.01, you don't just split it into 25 plus 0.01. No, you factor out the 25 completely, which leaves you with 1 plus 0.01 divided by 25. Then step 2, just ensure that your new x fraction is vastly smaller than 1, which in this case, it definitely is. And finally, step 3, simply bring the power, so for a square root that's 1/2, bring it down to multiply with your tiny x value. And just like that, a complex root becomes super basic algebra. And this brilliantly illustrates exactly why context matters in physics. Think about this specific number, 320 kilometers. When you're calculating the effect of height on gravity, the standard complex formula normally applies. But here's the trick. 320 kilometers represents exactly the 5% threshold of Earth's radius, meaning if the height of your problem is less than 320 kilometers, you are safely in the clear to deploy that binomial approximation cheat code we just went over. It brings the complex formula down to a wonderfully simple linear equation. Up next is section 4, the magic of triplets. Let's see how this whole concept builds into trigonometry. I actually like to frame these as pre-packaged power-ups that just save you massive amounts of time on an exam. So what exactly is a triplet? Well, trigonometric triplets are specific sets of 3 whole number values that perfectly satisfy the Pythagorean theorem. They essentially act as instant cheat codes for figuring out side ratios. But hey, remember a vital foundational rule before we get too excited here. Trigonometry is strictly valid only for right-angled triangles. If you don't have a 90-degree angle, these cheat codes simply won't work. Now, let's look at the most legendary of them all, the 3-4-5 triangle. In physics, the angles 37 degrees and 53 degrees show up constantly. But how do you actually remember which side goes where? Well, it's just simple logic. The rule is this: the largest side always faces the largest angle. So the hypotenuse, which is side length 5, faces the 90-degree angle. The side length 4 faces 53 degrees, and the smallest side 3 naturally faces the smallest angle, which is 37 degrees. If you can just visualize this relationship, I promise you'll never mix up sine and cosine values for these common angles ever again. But beyond the 3-4-5, there are definitely a few other essential triplet sets that you really should commit to memory. We've got the 5-12-13 triangle and the 7-24-25 triangle. Also, keep an eye out for direct multiples, something like the 6-8-10 triangle, which is literally just the 3-4-5 triangle doubled. Memorizing these specific alternatives allows you to look at a problem and solve those geometric ratios at first glance with just blazing speed. You get to bypass the Pythagorean theorem entirely. And finally, section 5, mastering the ASTC rule. We are now going to conquer the single biggest source of careless errors in all of physics, and that's getting the negative signs wrong in trigonometry. We can actually take a complex, highly mathematical set of rules and reduce it to a beautifully simple 4-letter acronym, ASTC. It stands for all, sin, tan, cos, and this brilliantly illustrates a mental model designed to instantly tell you which trigonometric functions are positive as you move across the 4 90-degree quadrants of a circle. Let's methodically trace this out together. In the first quadrant, from 0 to 90 degrees, all functions are positive. Moving to the second quadrant, up to 180 degrees, only sine and its reverse, cosecant, are positive. In the third quadrant, up to 270 degrees, only tangent and cotangent are positive. And finally, in the fourth quadrant, up to 360 degrees, only cosine and secant are positive. Now, did you notice something interesting there? Because all are positive in the first quadrant, every single trig function is mathematically guaranteed to be positive in at least 2 of the 4 quadrants. So, I want to challenge you to mentally map this out right now. If a problem gives you 180 degrees minus theta, visualize pulling back from that flat 180-degree line. You're firmly in the second quadrant, right? So sine is positive. If you have 270 degrees plus theta, you're pushing forward into the fourth quadrant where cosine rules. And remember, every 360-degree loop just resets the cycle entirely. By simply looking at the base angle, you can immediately identify the correct plus or minus sign without any second guessing. To wrap things up, the core message of this explainer is pretty simple. Physics is no longer this formidable boss that you have to be afraid of. When you wield these mathematical cheat codes with confidence, the landscape changes entirely. I mean, tools like converting logarithms, factoring properly for binomial approximations, spotting trig triplets instantly, and mapping signs with the ASTC rule. These are exactly the tools that bridge the gap between failure and absolutely crushing your top marks. So, I'm going to leave you with this provocative thought. The next time you sit down for a mock test or the actual exam, are you really going to leave a massive 4-mark physics question blank just because you ran into a messy 25.01 square root? Or are you going to use your new toolkit, apply your mental models, and utterly crush it? The choice is yours, but honestly, I think you're ready. Thanks for joining me on this explainer, and keep learning.
Stepping into this dimly lit, futuristic classroom, the air is kind of thick with anticipation, and the very matrix of the universe is literally about to be revealed. Today, we're not just going to stare at boring numbers on a whiteboard. No way. We're actually diving into the underlying code of reality itself. We're going to explore those absolute foundational tools that perfectly bridge the gap between abstract equations and our physical world. So let's jump right in. You know, the educator Amon Mathior hit the nail right on the head with this. He said, mathematics is the language of physics. You cannot speak to the universe without it. That quote, it's a total game changer. Seriously, math isn't just some annoying hurdle meant to trip you up on a midterm, and it definitely isn't just a prerequisite you have to suffer through. It is, quite literally, the only vocabulary the universe actually understands. If we want to know how stars burn, or how particles move, or how heat flows, well, we've got to speak the language, right? Which brings us to what you're about to become today, a decoder. Now, a decoder isn't just someone who painfully memorizes a bunch of formulas. Not at all. A decoder leverages mathematical tools like glowing holographic keys to unlock completely complex physical phenomena. You're basically about to upgrade your brain's entire operating system and master the absolute foundational tools of physics. Okay, moving right into our first chapter, logarithms, or the secret of calculations. So think of logarithms as basically the ultimate compression software for the universe. Before modern computers were a thing, logs were brilliantly designed to shrink these impossible, mountain-sized math problems into simple everyday additions and subtractions. And we kind of rely on 2 twin pillars here. First, we've got the common log, which uses base 10. That's the familiar standard, the one we use for everyday scaling. But then we have the natural log. This one uses base e, or Napier's constant of 2.71, denoted as ln. Now, this isn't just some random mathematical quirk. This is the actual language of nature. It's literally the base our physical world naturally defaults to when dealing with stuff like continuous growth, radioactive decay, and thermal physics. But here's the real question. How do we cross over from that abstract language of nature back into the simple math we can easily calculate by hand? Well, picture this specific number as a glowing vital bridge, 2.303. Whenever you're tackling complex thermodynamics problems, like say finding the work done by gas in an isothermal process, you literally just multiply your natural log by 2.303, and boom, it magically converts it right into a solvable common log. It's that simple. All right, let's build an even more powerful tool with Chapter 2, Binomial, making the impossible possible. We're upgrading from just compressing calculations to gaining what is basically a literal superpower, the ability to calculate the uncalculatable completely in your head. Picture this. You're sitting in a ridiculously high-stakes exam, the clock is ticking, and suddenly this terrifying numerical problem drops right in front of you. How do you find the exact square root of 25.01 without a calculator? I mean, for most students, this induces pure panic, right? They stumble, they just guess, and they lose precious time. But for a decoder, this is your moment to shine. So here's exactly how we break this beast down. Step 1. Do not, and I mean do not just write it as 25 plus 0.01. Honestly, that's a super common, tragic mistake that leads absolutely nowhere. Step 2. You actually have to mathematically extract that 25 out of the brackets entirely. Why? Well, that brings us to step 3. We are desperately trying to achieve this sacred 1 plus x blueprint inside the bracket. You absolutely have to leave a 1 behind. And once you've got that perfectly formatted holographic blueprint, step 4 is an absolute breeze. You just bring the fractional power down to create 1 plus nx. And that entirely illustrates the magic rule. The complex expression 1 plus x to the power of n smoothly transitions into 1 plus nx. But wait, there's a catch here. This powerful mathematical trick only works when the fraction x is vastly smaller than 1. That tiny, almost microscopic value of x is exactly what allows us to just drop all those higher mathematical powers and shrink the math into an instantly solvable format. It literally turns a nightmare root into simple basic arithmetic. How cool is that? Now, let's plunge into the visual matrix of physics with Chapter 3, Graphs, the real meaning of slope. You see, reading curves isn't just some dry exercise in geometry. It's literally how we watch the story of a moving particle unfold in real time. Actually, let me pose a bit of a trick question to you, one that honestly trips up almost everyone the first time they see it. When a particle's curve dives deep down into the negative y-axis, is the slope increasing or is it decreasing? Think really carefully about what your gut instinct is telling you here. Ready for the massive plot twist? Because there's a huge difference between these two worlds. From a strict math point of view, if a value drops from negative 0.5 down to negative 1.73, the slope is technically decreasing, right? Because the number is getting smaller on a standard number line. But from the physics point of view, that negative sign merely indicates direction. It's like a car speeding up in reverse. So the actual magnitude of the slope, the pure physical steepness of that motion, is actually increasing. Mind-blowing, right? So the absolute crucial takeaway here is to mentally map these 4 glowing archetypes right in your head. First, we have the smiling curve. Its slope is positive and increasing. Next up, the sad smiley, negative and decreasing. Then we have the upward arch. It's positive, but the slope is decreasing as it kind of flattens out. And finally, that super tricky downward slide. It's negative in direction, but its magnitude is totally increasing. If you just map these 4 clearly in your mind, I promise you, you'll never misread a velocity or acceleration graph again. Okay, bringing it all together now, let's head into our final chapter, the new perspective of physics. It's time to quickly take stock of what we've achieved here. Just look at the Dakota's arsenal you've acquired today. You now have logarithms to shrink literal mountains of raw data. You hold the 2.303 bridge to effortlessly conquer thermal physics equations. You've got that 1 plus x binomial blueprint to solve impossible roots straight in your head. And you're armed with the physics POV lens to finally reveal the true physical meaning of falling graphs. Seriously, that is a massive, massive upgrade to your problem-solving toolkit. So I'm going to leave you with this somewhat provocative question. Are you now ready to actually converse with physics? With all these powerful tools in hand, I really want to challenge you. Next time you face those upcoming numerical problems, don't view them as terrifying tests designed to break you. Instead, look at them as a fascinating, ongoing dialogue between you and the universe. Math is no longer a hurdle. It is absolutely your hidden superpower to decode the universe. Use these keys, trust the beautifully structured language of reality, and never, ever stop decoding. Thank you so much for joining me for this explainer. Until next time, stay curious and keep decoding.